All right, it's going to be a quick minute. So, welcome to this year's PTI convention and the PT Bridges and Multistrand PT Technical Session number 1. My name is Nick Amico, and I'll be your moderator today. PDH credit is offered for attendance at this session. To obtain PDH credit, you must attend all the presentations that are included in this session. On the PDH tracker form, you're going to enter both codes that will be provided during the session. Now, it's going to be a code is provided after the first presentation and the code at the end. You have to have both codes in order to get the credit, so you got to be there all the time. All right, we're going to jump right into it. Our first presentation is on specialized bridge post-tensioning assessments with Travis Green and Brian Merrill. Travis Green is a principal in the Washington, D.C. office of Wish, Janney, Elster & Associates with 24 years of structural steel and post-tensioning experience. Mr. Green is chair of the American Welding Society D1.1 committee. He is a past chair of the D1.7 committee. He's a member of the PCI Parking Structures Committee, Joints and Structures Committee, and Ports and Marine Structures Committee. Brian Merrill is a principal in the Austin, Texas office of WJE with more than 35 years of post-tensioning experience. Mr. Merrill is a member of several PTI committees and is also serving as one of 3 members of the FIB Task Group 5.13, Rewriting FIB Bulletin 20, Grouting of Tendons in Pre-Stressed Concrete. He was selected as a PTI Fellow in 2021. So, Brian and Travis, turn it over to you.
Good morning, everyone. Nice and early first day of the convention. Glad you're here today. So Brian and I are going to be talking about specialized bridge PT assessments. We have about 50 minutes for the presentation, a few minutes for questions, so I'll work through my slides first, and then Brian will come up and work through his slides. So before we get started, just some standard PTI language. This presentation complies with the Registered Continuing Education Program, so you can get CEUs or LUs out of that. And then also AIA requirements, so that's the LU requirement there. So standard language for PTI presentations. Again, this is just a standard PTI copyright material disclaimer. So we have permissions associated with the presentation. So what are the learning objectives? So we want you to understand what bridges might have grouting problems. We want you to understand what specialized assessment techniques you might be brought to bear for PT structures, particularly bridges for this presentation, and then what some general repair strategies might be. And then Brian's going to follow up with a fire damage external tendon assessment of a bridge, I think in Texas, right, Brian? So what are we talking about here? We're really talking about strand corrosion for the most part. So we've had a really good history of performance with post-tension structures. There have been some notable challenges over time. In this discussion, we're really going to talk about pre- and post-2000 bridges in the U.S. That demarcation line is generally what I consider to be, we have potentially grouting problems pre-2000s. We have less grouting problems post-2000. So if you remember anything from this presentation, this is probably the point. This is one of the learning objectives. So why did the pre-2000 bridges have some challenges, right? So we had different joint and anchor detailing back then. We were using neat cement grouts that had some bleed characteristics that weren't ideal. By the way, Wish Janney's done a bunch of testing. If you've looked at these kinds of grouts, you can see sometimes that when they segregate, they're white on top, and you'll see some photos of that later. But even that white grout can have relatively high pH values based on our testing. Obviously, we had some improper or incomplete filling. And then there were grouts at a period of time that used an expansive admixture, particularly for externals, that caused some HDPE problems. And then, so post-2000, right, we have had also a couple of different challenges, right? We had one manufacturer that ended up with elevated chloride contents in their pre-packaged grout. We still continue to find some voids. I consider them most of the ones that I've seen are minor. I call them lensing. And then we have had some soft grout, and that grout it basically doesn't harden or didn't harden, and that's been linked to excessive mixed water, high humidity storage conditions, and then high bleed characteristics. So what did we do about it, right? So the industry identified this as a challenge, and we started developing different materials and different details, right? So we start to use HDPE and PP materials, polypropylene materials. We start to look at encapsulated systems. We start to frankly pay more attention to how we're injecting the grout, right? And how well we're filling those ducts. We start to develop, this is a FHWA SNP on the right-hand side there. Right over here, right? Those are FHWA figures, and those show venting, injection and venting sequences for different configurations. So we got a little more careful about where we're putting vents and how we're opening and closing them. And we also changed the grouts, right? So we go from a neat, like a cement and water type grout. We then start to add cement and water and some expansive admixtures. We then go to pre-packaged grouts, which are kind of common thixotropic type grouts. And even now there's some flexible fillers that are being used. So this is a nice graph. This is a friend of mine named Bruce Osborne. Bruce has been doing bridge inspections like this for years, and so he put this together as part of an article in Aspire, but I think it's a good graphic, right? It shows that in the 70s, in bridges that he inspected in the 70s, you know, had both voids and some failures, right, over on the far left there. But as time went on, it shows that, you know, based on his observations, right, which are physical observations, that things tend to get better, particularly as we get kind of into the 2000 range. So this kind of, to me, reinforces the 2000 numbers seems okay. So what is a specialized inspection, right? So generally speaking, we're going to do a document review, like all engineers like to do. In that, we're going to understand what tendons are out there, straight, harped, external, internal, what their geometries are, what type of duct materials are being used. In many cases, as it relates to Wisciani, someone else will actually do a comprehensive visual inspection and identify the areas that are challenging, and even sometimes do mechanical or acoustic sounding to further delineate that before we're involved. But that's all part and parcel to, I think, the specialized inspection approach. So how do we deal with the tendons? How do we understand what's in the tendons, right? So there are openings, there's non-destructive testing that we can do, there's grout materials testing, and there's corrosion testing. So those are kind of I think the four pillars of this type of inspection process, right? And within openings, there's drill holes, which you literally drill a hole into the duct, and then there's more kind of concrete openings. For non-destructive testing, obviously GPR can help find tendons, either whether they're PP, HDPE, or steel. And then some people will use metal detectors. A lot of these big bridges, you can't really use a metal detector because it's too deep. And then there are folks out there who are doing impact echo, impulse response, and MIRA. That's that's tomography. They are using that system to try to identify voids, but again, you still have to confirm that NDE data. We consistently do grout testing on almost every one of these specialized inspections, and we choose whether we're going to do corrosion testing, and I'll talk a little bit about why that is in a minute. So these are some photos of some internal tendon ducts, right? So these are where you chip out, you cut the duct open very carefully, and then you start, for us, we document where the location is, what the grout conditions are, what the strand conditions are, what the duct conditions are, if there's moisture present or water present. I think my record on water is, I think, a 55-gallon drum out of a parking garage in Raleigh. Didn't work out too well for that. But so we'll document those conditions. This allows us to take grout samples, right, for materials testing. But again, and it allows you basically to see it. It also allows you to do HCP, half cell potential, or linear polarization resistance testing. And those repairs generally go back to, we're gonna, put the duct back, we're gonna try to seal the duct as best we can. There's several ways you can do that, and then doing concrete repairs on the backside. So we also can look at, for internal ducts, we can look at anchors and vent ports. So in the middle of the screen here, so this is the top side of a deck and you can see my Home Depot bucket where we were trying to figure out if the water was coming in through the concrete or around the block out. But in this case, what we noticed when we did the inspection we noticed some very minor efflorescence out of the duct in the inside of the bridge. We did some water testing. We found out that because the vent tubes, right, these guys right here, they weren't full. So water, when it hit the bridge, goes down the cold joint and the block out, goes down the vent tubes because they're not sealed, and gets into the tendon. Fortunately, didn't end up a big deal, but that's why we did that test. And then on the right here, these are anchor inspection openings. So in this particular case, this is a transfer girder, I think. And so we saw cut, chip out, and then we've drilled in one of the empties, we've drilled into the trumpet to see conditions inside the trumpet. So drill holes, this to me is the most common, visual inspection technique for specialized inspections. You literally locate the duct, you drill a hole in the duct, preferably at the top of the duct, because if you're going to have a grout void, it's going to be in the bottom. You insert a video scope, you look at those conditions, and then the video scope also helps you figure out how long the void might be in both directions, right, uphill and downhill generally. We document duct and strand corrosion. Relative to strand corrosion, there's a paper from PCI from Augusto Sasson, I think is actually how you say it. And so we use they have little pictures, if you guys have seen these. We use these pictures, and that allows us to have like categories 1 through 6, right? So we can get some numeric value so you don't have to go back to the picture every time, right, to look at the condition. We look for segregated grout and document that. We try to measure if there's moisture present and what that percentage might be if we suspect moisture is there. In many cases, there's not moisture there, so we don't do that testing. We check void length, and then I have our folks estimate the percent of the duct that's filled with grout. And so the length and the percent filled helps us define what the volume could be, right? So that when we're doing repairs, we can back check that. In these, virtually, you're never hardly going to get a grout sample out of these. And when I say grout sample, for those of you who aren't familiar, think like a golf ball sized piece of grout. That's about what you need to do this testing. Brian's smiling because I referenced golf in the presentation, which was good. You can do now half cell potential measurements with some small probes. They have some small handheld probes that you don't have to enlarge these holes. These holes are generally about 3/4 of an inch in diameter. It can't be an inch. So here's just some photos once you stick the video scope in and what you might see, right? So left, really no corrosion, but not full. Middle image, some corrosion or minor corrosion on the duct, but really the strands look pretty good. And then the right-hand side are some PVC ports that have been set where voids were identified so that we can prepare for grouting in the future. So, and just before I leave, once these are grouted and filled, right, once we fill them with grout, those ports generally get cut off, and then there's an inspection process afterwards for certain ones. So external ducts require a little bit different approach, right? Kind of similar ideas, but a little bit different approach. So we can do drill hole openings here, and we can do larger sheathing openings. So you basically take a hole saw and you can drill a hole through the sheathing, or you can partially remove or completely remove the HDPE pipe in certain areas, and then you can also obviously get to anchors and deviators as necessary. So with the hole saws, because those are the easiest, and you can see here on the left we've written down bleed trail entire length. So what that means is there's a small void that's on the top of that HDPE pipe, above the grout and below the entire interior diameter of the pipe. And generally they're small. They're 1/16, 1/8. They're not huge voids, but they're there. And actually you can find these if you take a hammer and tap, a lot of times you can find these. We've even tried to use thermography to find them, but it's not as reliable. So we don't take grout voids typically out of the holes. We will take grout voids out of the larger openings on the externals. Again, we're going to look at strand corrosion. We're going to look whether the duct is cracked, right, or damaged in some way. And then we're going to qualitatively say whether the grout is white and powdery and flaky. Is it dark, hard? Is it wet? Those kinds of things. We may do some half-cell potential measurements and linear polarization tests as well. So these are a series of photos of a location where we've stripped the sheeting off, right? And we have extracted some grout samples, right? Because you see that missing grout. So we've taken some grout samples. We've also done carbonation testing, and we'll do that typically to look at grout quality. So the purple there is carbonation testing, right? And then on the right here, right, we're doing corrosion testing, half-cell potential measurements in this case. Brian, I think I have about 10 more minutes. So on the repair side of the externals, right, so for drill holes, what I've seen, and I think this varies across the industry, they'll take a piece of the sheathing, cut it, and then embed it in sealant. I've seen that. The more common one I've seen is they'll do thermally set HDE plugs, where they basically get a plug down in there and heat it up and it fuses, and then they cut it off. There's also grouting and taping that can be used, where they basically put the clamshell back together, they grout it full, and they tape it up. So there's kind of multiple versions of that story. At anchors, which are on the bottom here, right? So once they get it open up, often they'll get like a corrosion inhibitive coating. They'll get a grout cap. Sometimes that's a little bit of a challenge because they didn't have a grout cap, so you have to kind of figure out how you're going to install the new grout cap onto the old anchor plate. You'll re-grout those. We'll put the concrete block out back, and then put coating back over the top. So once we've gathered all this data in the field, you will take that back. We have an in-house laboratory where we'll do petrographic examination of the grout, right? So what does that tell us? It tells us what's in the grout, right? If it's just cement, if it has fly ash or sand. It'll tell us if it has air void characteristics, if we're interested in that. It'll tell us if it has any kind of deleterious reactions like DEF type things, or excessive gypsum or whatever. It'll tell us if it has cracks or corrosion staining, and then it will also measure pH and moisture content out of that. And so on the right here, right, so these are just very close up air voids. These are etronite rings, etronite would have rings around them. No, I'm sorry, this is the etronite, and then this is the fly ash particles that have rings around them. So, it is useful in that sense. We'll also do chloride content analysis. So my default is generally acid-soluble chlorides. That gets all the chlorides out of both aggregates and cement. So it gets you everything. It can result in a little bit higher number than you could get if it was just water-soluble, which is generally what's available to the steel. And there are several different corrosion thresholds that are out there, and you kind of got to pay attention to what the metrics are associated with those. ACI is 0.08%. Acid-soluble weight by cement. FHWA, I think with Wisjani did some of this testing, I think in around 2014. They've come up with two different metrics here. So 0.4 acid-soluble by weight of cement plus water for initiation, and then 0.8 for propagation. So there are different metrics, and you got to be careful about which one you're using there. There also are studies that show that there have been times that we've had corrosion in strands without elevated chlorides, and so people have started to dig into what is this really, what's happening here? So Federal Highway has said that sulfates can be every bit as damaging as chlorides if there's moisture present and there's low pH in the grout. So there are now tests, so there's a total sulfur test, but I think more likely you're going to end up looking at, if you're doing this, you're going to look at the FHWA test. So that's a free sulfates type test that has been recently introduced into the industry. So I think if I were you, if I'm looking at, I'm interested in sulfates, I'm probably starting to look at that FHWA test. So on the corrosion side, right? So the two primary methods that we use to look for corrosion are half-cell potential measurements. Those are used in many different types of concrete structures, and linear polarization resistance testing. So they use the same electrical connections. They're different, technologies essentially, or tests. So HCP, if you get very negative values, can be indicative of ongoing corrosion. Linear polarization testing can give you kind of the corrosion rate, like how fast is it corroding. So HCP tells you, hey, is it happening? Linear polarization says it's happening really fast, right? So the challenges with these ducts, right, and like all pre-stressed structures, frankly, is you don't know if is it the galvanized duct that's corroding? Is it the strands that's corroding? Is it the bars that are touching the ducts, which are touching the strands, or those are the ones corroding? So you do have to be a bit careful about how you use this data. There are also some modifications based on the amount of the multi-strand systems that you engage in the test. So there's just some complexity there. So are repairs required? In general, my mentor, Mark Moore, would say, I would rather have the duct fully grouted than not. I think I align with that viewpoint, but there are times when you either can't grout it or it's been determined that they don't need to grout it. So when we were working on the Central Artery and Tunnel project, the Big Dig project, we learned that they actually, when they had voids in their ducts and the strands were not exposed, they elected not to grout those strands. Whereas many DOTs that I've worked with, if there is a void, they are going to fill it. But you may not actually need to, depending on certain exposure conditions. So what goes into that? There's not a ton of industry guidance right now about it, but what we try to think of is, how important is this tendon? How many tendons do I have? How many strands within the tendons do I have? Is this an ongoing problem? Was this a problem that occurred a long time ago? How bad are the grout metrics, right? Or do we have like no grout, lots of water intrusion, heavy strand deterioration, and have a tendon that is super important? Then we're probably going to have to repair it, and that might not be limited to grouting. But I think you do have to kind of think through what you're planning to do there, because the repairs are expensive and time consuming. So what are some common repairs? So the two highlighted here, right? They're the most common for my book. So you're repairing pourbacks and coatings at anchors. You're trying to protect anchors and joints, basically. And then grouting repairs. There are other repairs. For example, you can do kind of waterproofing detailing around some of these deck, areas, or you can flood coat. Some Midwest states are starting to flood coat and sand, broadcast sand into those flood coats, that like methylmethacrylate or epoxy type materials. There's impregnation techniques that people are using. Those are generally silicone-based materials. And then if you have to do some strengthening, right, there's obviously external tendon installation, even if it wasn't originally intended to be an external tendon bridge. And then there is more and more discussion about CFRP repairs on these bridges, although what I've seen on bridges is really related to shear and not flexure. But there's more and more discussion about using CFRP to repair some of these issues. So this is just an image of the pourback details, and I'm going to move through this a little bit faster to give Brian plenty of time. In this slide, I'm really focusing on remedial grouting. So there's three flavors of grouting is how I think of it. So there's vacuum grouting, right? That's where you pull a vacuum and you allow the grout to be pulled into that vacuum. There's pressure-assisted grouting, where you're basically pushing from, let's say, the low end of a void, and you're pulling from the high end of the void, so you're pushing and pulling the grout through the void. And then what I find the most common is pressure grouting. So that's basically, you've installed these ports like you saw earlier, you're going to inject from low to high of that void, and then you're going to do that under pressure. You're not going to try to use a vacuum. So there are quality control measures that are commonly used, right? So we're going to look for ASBE certifications. We're going to check bags to make sure it's the right material. We're going to check bag dates. We're going to look at how much water is added. We're going to do mud balance testing, flow cone testing. We're going to take cubes for compressive strength. We're going to document grout and ambient air temperatures. During grouting, we're going to measure grout volume, and then after grouting, we're going to probably drill out certain numbers of ports so that we can confirm that they have been fully have been filled. And then we're also going to check to make sure that the grout compressive strength is reasonable. So with that, we're going to go into a case study.
All right, good morning. So this is what most people think about when you talk about fires on bridges. When I was at TxDOT, we got about one every 3 or 4 months. A tanker would catch fire. That's not what I'm talking about this morning. I'm going to be talking about a fire inside a post-tension box. We actually had 2 of them on the same family of bridges. And you can see this is one of the interior shots before they got it cleaned up, and it was quite a mess. So we actually had the 3 bridges I looked at. We had 3 locations in 2 different cities in Texas. In each case, trespassers, vagrants, whatever name you want to apply, had defeated the access hatch. Sometimes they put their own locks on the access hatches and were occupying the bridges for various activities, most of which involved some sort of cooking. Only 1 fire was reported to the fire department. The rest of them were discovered after the fact. 2 of them were noticed during routine inspections. They recognized that the access hatch had been modified, and so they went up in there and found the mess. There were no reported injuries, but we did have some tendon damage in 2 of the bridges, and I'll talk about those in the next few slides. So the first one was a ramp span. Traffic was on the span during this fire. The fire department was called to this location. There was smoke reported coming out of the expansion joint, out of the access hatch. What you might be able to see, what I've shown in the yellow circle is some webbing, some strapping that the inhabitants had used to haul their material up and down into the box. What we believe started this fire was an air conditioner that they had hauled up in there and wired into the bridge lighting system, but the voltages weren't compatible, and so it started an electrical fire. And it got pretty hot. There was a lot of damage to the main external tendons. I'll show you the tendon arrangement here in a slide or 2. And there were lots of other materials and equipment in that span that some of which caught fire, some of which didn't. The interesting thing though is that, and I mentioned there was traffic on the bridge during the fire, post-fire there was no settlement, there was no deflection, there was no opening of the joints, nothing. You could not tell externally that something had gone on inside. So this bridge was part of a span-by-span segmental bridge. It was a 4-span continuous unit. This was the end span. It had 4 internal drape tendons in the webs and 4 external drape tendons inside the void. I mentioned that there was no cracking or deflection, so here's a few photos of what it looked like on the inside. A few of the strands did survive, but largely not many. The top slab tried to crush and tried to collapse. Due to the heat. This was a pre-stressed transversely top slab, so all those strands let go. There's where our tendons used to be. There were 2 on the left, 2 on the right. They're gone. If those guys were in this when those tendons let loose, I imagine it was terrifying. They were 19-strand tendons. So here's a tendon arrangement in the elevation view. The blue are the external tendons. You can see we've got the continuity tendons going over the top of the pier here. And so that helped this structure survive. If this had been a simple span structure, it might not have made it through the damage. Cross-section of the bridge looks like this. You have the half-inch diameter pre-stressed strands at 7 inches across the top. I show the blue externals. Actually, they were 12-strand tendons, my apologies. And the internal tendons in the webs. And those are the ones we lost. And so this one actually was a pretty easy decision. The DOT decided that they had so much damage to the tendons, and the damage to the pre-stressed top slab was probably the primary driver of this, because we could have replaced the tendons. We had no real good way to replace and repair that pre-stressed top slab. So they decided to shore the bridge and take it out as part of a reconstruction of that 1 span, and they replaced it with a simple span pre-stressed concrete girders. The second location, though, is a little more interesting because we actually got to save this span. This was a ramp span. They don't know how long it had been since the fire had occurred. They suspect it was at least 3 to 4 months that live traffic was on this span after the fire. This one, the fire department was never called. They never noticed the smoke. They did lose one external tendon, but the other 3 remained in place. Similar to the other span, there was minimal damage to the concrete. And I'll show you some images, and if you see grout that was removed, that was done during either our assessment or by the DOT's cleanup crew, but all the grout remained intact on the intact tendons. And once again, no cracking, no deflections, no external evidence of any type of distress to this span. So here's the inside of this one. Similar cross-section and design. Actually, they were designed under the same original design contract back in the middle 80s. What we've got here, the 2 tendons on the left were judged to be in pretty good shape. They had minimal damage to the plastic or the polyethylene duct, but no other real damage to the tendons. The upper tendon on the right is the questionable one. That's the one we're not really sure about, and that's the one we're going to do a lot of investigation on. And this one was gone because there was literally a fire right on top of that deviation block that heated up and snapped those tendons. I say a fire, there were 3 fires in this box. So this one was shored to remain open during traffic. They kept it open during the whole process of our assessment. So we designed the shoring that you'll see here in a little bit. And then our assessment, we're looking at now at the concrete, we're looking at the grout, we're looking at the strands, the duct, the joints, everything, the epoxy segment joints, not the expansion joints. And as I mentioned, we found that there were actually 3 fires in this location, and we were working for Volkert, who was a design consultant who had been retained to develop repairs to fix the span based on what we found. And our question was, how bad is that one remaining tendon? What does it look like, and can we keep it? There's the shoring. Here's the interior of the box looking at the abutment. Now, we have a fire protection unit in WJE, and we're very fortunate to have those guys. And so I showed them some of these pictures, and they were able to walk me through where the fire was hottest, where versus it was not quite as hot. And basically they said that this condition here, where it's really a white colored or concrete colored appearance, that's where the fire was hottest. It had less soot. And if you can imagine, if you've got a fire pit in the backyard, as the fire begins to go out, it generates more smoke, hence more soot. So the hotter the fire, the less soot you have. And so this was one fire that got pretty hot. It didn't actually cause a lot of damage. The spalling in the concrete was minimal, was maybe a half-inch deep at the most. There was no tendons in this area. They all anchor way out here on the edges, so there was no damage to the tendons. But that was fire number 1. Here's a section of the grout on the tendon we were concerned about. No, actually, this is one of the good tendons, and that grout had been removed. So you can see the cracking in the grout. There is no duct on that tendon. It's been melted off or burned off. I'll show you what that looks like later. And that was where we had chipped out the grout to expose the strands, and they were in actually pristine condition. They had been undamaged, and I'll walk through our grout testing protocol here in a bit as well. Here's another location. You can see where the polyethylene duct had melted. This had already been cleaned up by the time we got there, but there was still a bit of residual items in there. We found a couple of shotgun shells. We actually suspect they were using that to start their fires. Crack open the shotguns, the shells, use the gunpowder to start their fires. Either that or it's protection, but take your pick. And this is an interesting photo, and I hope it shows up well. Let me see if I can get the arrows to show up. There we are. So some of these strands they necked down almost to a pinpoint. So if you can imagine a strand under tension, it gets hot, it begins to relax, it begins to elongate, and it's going to fail elastically. But once some of these strands, and roughly half of them failed in that manner, the rest of them failed with a blunt fracture. So in other words, all that force is now transferred to the remaining tendons, and they just they didn't have a chance to yield, they just ruptured. So we had a little bit of necking, a little bit of an early release, and then a violent rupture towards the end. And we took a bunch of samples of these to the lab to test. So on the concrete assessment, we did a rebound hammer, which is not my favorite tool, just because it's impossible to correlate a rebound hammer number to a compressive strength, but it is a pretty good tool for a relative comparison of a large area. And there's a testing protocol, and you do, I think, 16 little impacts at each location, and you take out the high and the low and do that sort of thing. And we were looking for areas of surface weakness, right? So that we could focus our coring and concrete petrography efforts in those locations. For the grout, we took some samples. We'll do some petrography once again in the lab, looking for the degree and depth of heat affection of that grout. So we can determine which strands might be more greatly affected by the heat. We removed some strands and tested them to failure to understand the properties of those strands. And we also tested some duct samples in an attempt to correlate duct condition to the heat that the tendon saw. And all of this was geared towards how hot did the strands get and can they stay in place? That was the ultimate question we were asked to provide. So there we are, that's Lane, my technician cutting strands. I had a question, I made this presentation a week ago or so on another conference, and I was asked a question about PPE. It was really dusty and sooty in there. It was also a little bit warm. We were wearing the full masks and the full respirators, and we were overheating. So we ended up, on the next day, got a little fan ventilation system to take the dust out of there so we could just wear an N95 mask instead of the full respirators. So we could actually operate in the thing because we were gonna hurt somebody. But there we are cutting. We ended up taking 19 samples to the lab of the strands for testing. There's James. I felt sorry for James. James is 6'4". The inside of the box is 4'7", and he's doing the rebound hammer across the surface for about 30 feet. We wore James out. He's a young fella, but we wore him out. Once again, we're taking our own cores. We've done a GPR to locate the reinforcing steel. This is a location near the hottest fire where we felt the concrete had the most significant depth of damage due to the heat. So, and we also took cores in the other end of the bridge that was unaffected by the fire so we could get a comparison, right? Because we're looking at damage versus undamaged. And here's a shot of the strands and some of the grout we removed. We ended up sending 4 grout samples to our laboratory. 3 of the samples had been affected by the fire, and 1 was from a location unaffected by the fire so that we could do a comparison. And we had to do some additional testing of those samples to kind of get a fingerprint on what that looked like. And I'll show you what that involves. Here's a shot of the grout, and if we had a darker room, it would show up. This area is nice and gray, but above this red line, and that's about 3/8 of an inch, it was more of a buff color. There was definitely a color change in the grout where it was affected by the heat, which you would expect to see. But it's different than concrete, right? Because concrete, when it's exposed to heat, typically it's the aggregates that change color. And I'll show you a slide of what that looks like. And the petrographers are very good at determining the impact of the heat on concrete and how hot it got and how deep it was by looking at the aggregate colors in petrography. But grout's a little bit different because there's no aggregate in it. So what we did was we took some of our unaffected samples and we cooked them at various temperatures for an hour to try to develop that internal heat damage of the grout samples so that our petrographer could have a fingerprint to look for on our heat affected samples, right? Because we needed to know how hot those grout samples got. And we did petrography on all the samples. So these are our cleaned up field notes. That's not how we did them in the field, but these were for our report. And so it's a little hard to see, but fire number 1 at the end of the bridge was right there. The big fire was right here with the tendon that failed. And then there was a third smaller fire on the opposite deviation block that we were able to find that TxDOT wasn't aware of at the time until we got in there. Here's our rebound hammer tests. And like I said, we were looking for deviations in the numbers so that would tell us where a hot spot was versus some others. All of these were cast roughly at the same time with the same concrete mix, so we weren't worried about variations in concrete mixes. But we didn't get a big deviation using the rebound hammer. So I mentioned concrete petrography. So our guys are really good at looking for these changes in colors in the aggregates. So the orange color, they call it pinking in the petrography industry. The paste will begin to pink, the aggregates will turn orange or almost a rust colored. There'll be lots of micro cracks and fissures in the concrete because as the concrete heats up, it's actually cooking the moisture out of it, and it causes it to crack and fracture. And from that, they can deduce the depth of impact of the heat on the concrete. And you can see we're zoomed in pretty close here at 2.5 millimeters. I mentioned the grout's a little different because we don't have the aggregates to give us that color telltale. So once again, now we're looking at changes in the amount of calcium hydroxide they can see. So calcium hydroxide is the main residual component left of cement hydration, and it gets cooked off during a fire. And so they were looking at, lines, differences in calcium hydroxide, as you can see by the red lines there, to determine the effective depth of heat on those two grout samples. And you can see we cut several of them up into quite small segments so they could do a detailed petrography on that one. For the strand testing, we pulled all 19 strands. Some of them we pulled really close to the heat-affected zone, and some of them we tested a little further away. We found that anytime we gripped within about 2 feet of where the strand failed, it failed in the grips. But once we got further away, the strand properties improved greatly. And so you can see here, we had a couple of them that were fairly low. This test 2 was really close to one of the fire locations. But all in all, the strand ultimate strength wasn't that bad. Over here, our metallurgy guys, there's been a lot of studies on heat effects on structural steel and a little bit on rebar. There's been less on strand, but they were able to provide me with some information and some test results. Basically, what we're trying to do is figure out what the temperature was in the strands that would cause them to rupture, right, based on our assumed stress level at the time of the fire. And then the other thing we're doing here is now we're trying to look at what degree of relaxation or loss of pretension would occur at some of the levels of temperatures we were finding, which are roughly in this 450 range Celsius. And you can see we're somewhere in there in this range of between, a little bit below 0.8 and somewhere around 0.9. So if you take the initial stress in the tendon, you could say, well, we've got a 10% reduction in the force in that tendon due to this relaxation due to the heat. And so that's something now that the designer can work with. I mentioned we tried to use the ducts as a way to determine how hot the tendons got. So once again, we cooked them in the oven at various temperatures to see if we could mimic what we found, and we never did get there, right? Because you saw that one where it was dripping off. Well, we didn't get there even at 600 degrees Fahrenheit, and that was cooked for an hour. We did find out that they ignite, and they burn very slowly all by themselves. And so that's what caused the ducts to just melt off. And that also caused a lot of our soot. So the ducts burned off. They burned off very slowly, and it's fire, but it's low heat, right? It's not a raging inferno. But they cooked off very slowly over time, we think. And so that was not usable as far as determining how the tendons were affected by the heat, just because the ducts themselves were on fire. So our conclusions, and it worked out pretty well for the DOT, the concrete was relatively unaffected. We weren't concerned about that pre-stressed top slab, which was the main thing that caused them to reject that other span. The strand temperature during the fire, at the main fire, the biggest fire, was less than 450 Celsius, determined from our petrographers, so that's good news. That tells us that the other strands, which are at lower temperatures, were likely less affected or almost unaffected by the heat. Some of the strands, as I mentioned, were directly exposed to fire, which caused their failure, and then others snapped because the load then transferred to the remaining strands, and they couldn't carry that force. The ultimate strength in the tendons, so FPU, we determined through testing was not going to be a concern. There was a possible loss in residual pre-stress, so that's FPS in the codes, and we estimated that between 10 and 12%, and once again, that's what Volkert was able to use to reanalyze the span, and they were able to go in and redesign a new tendon with a few extra strands, because we're replacing all the anchors, and make up for the lost force with no reduction in capacity. We did consider this was a ramp span, we did consider blocking off some of the width to reduce the traffic volume, but that turned out to be unnecessary because of our findings and Volkert's analysis. So they kept the span, they're replacing the failed tendon. They did do, as I mentioned, a refined analysis based on the results of our testing that gave them the way to estimate the force in the tendon, and due to the heat relaxation, and it's actually being repaired as we speak, I believe, down in San Antonio. So that's all that Travis and I have. We'll be happy to take some questions. We finished 5-7 minutes early, so that's always good. Do we have any questions for either Travis or myself? Yes, way in the back.
So when Travis was speaking about the voids found during the big dig, he said that they often keep those voids there not to grout them. What was the justification behind that?
You want to grab that mic there?
Sorry, Jason. Guess I was supposed to bring you the mic. Say that one more time for the group.
So Travis had mentioned it during the big dig. There were some voids found in the tendons, and they were opted to just keep them as voids and not fill them with grout. What would the justification for that be technically? I mean, how or benefit?
Good question, right? So what they basically thought was, listen, we don't have water intrusion, right? But they're saying that they do have grout to passivate the surface of the steel. And because they have that grout on those strands, they're not going to fully fill that space. But if you don't have that grout to passivate the steel surface, then they were thinking they would grout.
Saw another hand back here.
There was another hand.
Not that I don't trust your work, but what bridges are these in San Antonio?
It's on the I-35, I-37 San Antonio Y project. And I was hired because I was on one of the original design teams at TxDOT and also was involved in its construction for about 7 years. So I'd been in the bridge a number of times doing a routine inspection, so I was probably more familiar with that bridge than anybody around.
Were you cooking in that bridge?
I was not cooking in that bridge. Oh, I was cooking with the mask on. Anybody else?
Sure, I got a question for you. So there's another project that had grout voids in the tendons, and the client opted to fill those grout voids, and then a few years later had tendon ruptures at those locations. And one of the theories that was explained was that there was an issue with dissimilar grout materials at that spot that caused part of that. Is that a thing? Or if so, can you speak to that?
You want to? I can. Yeah. Okay, I can speak to that. So, and so the San Antonio Y is a good example of that. TxDOT went in 2010 and opened up a bunch of tendons because they knew they had voids. We'd gone through that bridge when I was still at TxDOT, and we knew that roughly 40% of the tendons had voids of some type, and some of them were actually completely ungrouted. They'd forgotten to grout them. So we went through and actually, when I was at TxDOT, hired WJE to go in and sample the grout and test it. And so Travis mentioned that white chalky grout that sometimes forms in some of those earlier bridges. And it doesn't have the compressive strength you'd like it to have, but it actually still has a very high pH. And so we actually did some compatibility testing of that high pH but chalkier grout and found it was still compatible with a newer grout at similar pH. What I think you're referring to, though, is a case where they ended up developing soft grout due to the segregation of the grout, which has an elevated sulfate content. And the problem with the sulfates is the sulfates chemically prohibit the passivation of the steel by the high pH matrix. And so you end up with a section of strand that's unpassivated right adjacent to a section of strand that is passivated, and there you set up a corrosion cell. And it's a very aggressive corrosion cell because it's almost like putting, a positive and a negative pole on a battery real close to each other. So I think that was the case. I'm familiar with some of those.
There's probably one other one that we're
Right.
not. But and Federal Highway's done some research recently on dissimilar grout materials. And And I think the one you're talking about, if I remember right, there's a suspicion that some of that remedial grouting didn't have very good material properties, right? Gypsum-type material that absorbed moisture. We do this kind of terrarium, electrochemical cell starts to happen, and we get corrosion at those locations. So there's a couple variations of that story depending on the particular bridge we're talking about.
Gotcha. All right, fair enough. Any other questions out there? Okay. Hey,
Thanks,
you
guys.
very much.
Appreciate it.